All right, let's begin. So we're in a weird room yesterday. I didn't want to record anything. So from now on, I'll record. I'll send you guys the link. And first class is kind of an intro class. They're all the same. I'll just post a video from the last intro class to this one. But for now, let's actually move on. Let's do some calculus. So we're going to talk about part one of our course. Fundamental techniques of integration. So we're going to spend a few weeks on this. About a lot of different integration techniques. Maybe picking up from Calc 1. One of the last things you guys did was integration by substitution, usually. So let's talk about the art of integration, because as you're going to realize from this course, there's definitely an art to it. So you're faced with some integral of f of x dx, right? So some random integral shows up on a test or a quiz or just something that you're interested in working on. Okay, there's an integral. How do you go about computing it? How do we compute it? Okay, so step one, when faced with any random integral. Try to apply a basic rule. What's a basic rule? So in Calc 1 you learned about a lot of integration of some elementary functions. Basically you reverse the derivative rule. So these are just things that you kind of know by heart by reversing a derivative rule. So that's like integral of x to the n is x to the n plus 1 over n plus 1 plus c when your n is not equal to minus 1. The integral of 1 over x is ln x plus c. Integral of the sine of x is the minus of cosine of x plus c, etc. Right? So you have a bunch of rules like this. Just some formulas that you have in your head that are memorized. I call these the basic rules, quote unquote. So it's just the integral of several familiar fundamental functions. So you should have a list of these rules in your head. So you're faced with a random integral, the first thing you're going to do is, hey, does this look like a rule that I've already memorized? And if yes, great, you just apply the basic rule and move on. But of course, you will never be in that situation all the time. In fact, in Calc 2, I'm never going to ask you something where it's just straightforward, a basic rule. So the next thing you try to do is you would try to simplify so that you can apply a basic rule. So sometimes an integral comes to you and it doesn't look like something you have memorized, but let's say right? So you see that, right? Now, one thing you'll try to think, well, is there a basic rule that I know that can deal with that guy? Well, no, there's nothing really that looks like that. This is a very relatively complicated rational function. However, there's a single thing in the denominator. I can just divide it into each part. Right? I can divide x4 into that, x to the fourth. I would get 1 over x. Divide x to the fourth into this. I get 2 over x squared. Divide x to the fourth into that, you get 1 over x to the fourth, dx. And now that looks like a basic rule. Well, I mean, you rewrite it a little bit. So I'd write this as 2x to the minus 3 and plus 1x to the minus 4. And now you'll notice that these two parts here look like that, and this looks like that. So I can now apply a basic rule to figure this out. Add 1 to the power, so that's 2x to the minus 2, and divided by minus 2. Add 1 to the power, you get minus 3, divide by the new power, it's 1/3. plus c, so you can figure that out. So those are the two first things you would have thought of in Calc 1, and it's no different here. These are always the first two things you try to think about when you're faced with a random integral. Does a basic rule apply? No. Can I simplify it to use a basic rule? Then if it's yes, it's good. If no, the third thing you're going to apply is try substitution. Now, this step was pretty obvious in Calc 1 because in Calc 1, this is the only other technique you knew about. So if those two didn't work, yeah, obviously that's going to be the answer. But substitution continues to be one of the easiest techniques to apply even beyond Calc 1. So pretty much if you're in some strange situation, one of the first things I would try to think about if these don't work, can a substitution work? Can I say u equals something and does that make it easier? And I'm going to assume you guys know the intricacies of substitution, how it would work. So something like, say, x cubed times the fifth root of 4 minus x to the fourth dx. So that's something that it doesn't look like a basic rule. I also can't simplify that to look like a basic rule. I've seen mistakes like people raise this to the fifth root and that to the fifth root and add them together, which is distributing powers across sums, very illegal. So this cannot be simplified. But you could actually get away with a substitution, u equals 4 minus x to the fourth, and fix that guy, right? So you basically want to substitute u or some other variable, it doesn't always have to be u, for an expression that would make the function simpler, as well as the derivative is somewhere else in the function. That's kind of optional. As well as it will transform the function ultimately into a basic rule. Yeah, so that's kind of where Calc 1 ended. And 4, we'll finish this list now. I'm going to give you a bunch of techniques that will come after this point that can help you figure out how to compute certain integrals. And there are techniques that exist besides the ones that I'm going to show you, but these are the fundamental ones. Pretty much everything after this point is almost a variation on these guys. So the first one that we're going to look at, the first new technique to compute an integral that we are going to look at is called integration by parts. And this is section 7.1 in your textbook. Integration by parts. Now, as you would have learned in Calc 1, substitution is really a way to reverse the chain rule, right? So remember the chain rule from derivatives. Substitution was the method that you could use to actually undo a chain rule derivative. Integration by parts is the reverse of the product rule. So if you have two functions multiplying by each other, we know how to differentiate them. We're going to use the fact that we know how to differentiate it and the fundamental theorem of calculus to figure out how to integrate a product of functions in certain situations. Recall, we had the product rule last time where if we had f of x times g of x and I wanted to take the derivative, we knew how to take that. This was f prime of x times g of x plus g prime of x times f of x. I'm not going to write the of x, I'm kind of. So basically we had f of g, if you wanted to take the derivative, you had f prime g plus f times g prime. Okay, that was the product rule. Here's what we're going to do. Let us take the integral of both sides. With respect to x. So I'm going to integrate both sides. Now, fundamental theorem of calculus tells you that the integral and the derivative are almost inverses of each other. If you integrate a derivative, you just get the original function back plus a constant, right? So there's going to be a plus c. I'm not going to write it, but just know it's going to be there. The integral and the derivative, they cancel each other out. And so this will give us just f times g on this side. On the other side, the integral of a sum is the sum of the integrals. Integration distributes across sums. So this is going to be the integral of f prime times g plus the integral of f times g prime. And now what I'm going to do is I'm going to solve for one of these guys. Just because I feel like it, I'm going to solve for this one. So this means that the integral of f times g prime is going to be equal to, well, f times g. And I'm going to subtract that minus the integral of f prime g. And of course there's a plus c here, but I'm not really worried about that right now. And that's the integration by parts formula. Usually there's a notation changed here. If I set u equals f of x and I set v equals g of x, then my du would be f prime of x dx, and my dv would be g prime of x dx. And so the above becomes well, my f is u, and the g prime dx is dv. So the above would become the integral of u dv equals u times v minus the integral. Well, this is v and that's du. v du. This is called the integration by parts formula. This gives us a way to integrate things that look like this. If you notice that you have one function and it's being multiplied by the derivative of some other function, you can figure out what the integral of such an expression would actually look like. It's going to look like this expression. And of course you realize that this expression has another integral in it. The good thing that potentially happens here is that this integral over here is going to be easier to compute than that integral over there under the right conditions. Right? But this is called the integration by parts formula. It's something that you should memorize in whatever way. I don't really have a nice mnemonic for it. Just remember it. So that is your integration by parts formula. Let's actually apply this. Example. Let's say we wanted to compute the integral of x times e to the x. That's one I asked you about yesterday. Let's actually see how we would actually do this. Now, I still want you to think. Basic rule? No. Can I simplify this to use a basic rule? No. Does a substitution work? Maybe. It turns out it wouldn't actually help here, though. Wouldn't help. But you could do a substitution here. So u equals e to the x would be pretty much the only thing that's valid here, because u equals x is always a bad substitution. It's never a good substitution. But if you do that, you'll end up with the integral of, I think, ln of u, and technically we don't know how to integrate ln, not yet. In fact, we're going to derive the integral of this using integration by parts. So, I see this random integral, I still go through this in my head, even though I'm not writing it, I'm thinking all this, but eventually I'm going to set on by parts. Now for us, it's going to be the answer because that's what I'm teaching you, but in general, you're not going to know, really. It's something you're going to try. Okay? So by parts really comes in handy when you realize that you have two functions being multiplied by each other that you want to find the integral of. And it's especially useful when you have two completely different classes of functions. Eventually I'll go back to that list that I started at the beginning of class and I'll complete it and tell you when you would want to try which technique. But verbally I'm just telling you now, that's when integration by parts would kind of be something that you guess might work. I have a product of two things and they're different kinds of functions. I have a polynomial times an exponential, right? If I can't do a basic rule or a simplification or a substitution, then integration by parts is probably what I would think. Okay, so now how does the integration by parts actually work? You want to compute the integral on the left side by doing the computation on the right side. Notice that on the left side there are two things that you need to know about, a u and a dv. And so step one in the integration by parts is you're going to make the choice. You're going to choose the u and the dv. So in this case, I'm going to make the choice. Does anyone want to make a choice?
Would it be easy to make the x du?
Let's say u equals x. And consequently, your dv will be e to the x dx. Okay? So I've chosen the u and the v, which means now I need to know the u, the v, the du. Which means I'm going to have to differentiate this. So du would be derivative of x is just 1, dx. And I'm going to integrate this one. So after making the choice, I compute the derivative and the integral respectively. Integral of e to the x, well, that's just e to the x. And 2, plug into the formula. So in this case, how would this look? I'm going to take the u times the v. Minus the integral of the v times the du. In this case, the v is e to the x. The du is just 1 dx. So that is just 1 times e to the x. So this here is u, v, minus the integral of, well, this is the v and the du. Integral of that. Okay. So you just pretty much plug that in. And now what you're going to notice, is, well, that integral, I mean, you don't have to write the 1 here. Now what you notice is that this integral on that side is a lot easier than this integral. In fact, that integral is a basic rule. We have that memorized, right? What is the integral of e to the x? It's just itself, e to the x plus c. And that is going to be your answer. And you can check for yourself. Remember, if you differentiate the answer, you should get the original integrand. Differentiating this by the product rule, you'd have x e to the x plus e to the x. Then derivative of that is minus e to the x. The e to the x's will cancel. You'll get back x e to the x. That's actually the correct answer.
Wait, I have a question.
Yes.
Wouldn't it be minus c because it's minus the integral? So like.
Yeah, but minus c and plus c
Oh,
don't
yeah.
really matter, right? It's just a arbitrary constant here. You'll need more information to figure out what that is, and it'll work itself out with the signs. So you don't really need to worry about that. But that's basically it. So, faced with a random integral, you think these things. Eventually, if you settle on maybe it's a by parts, you need to do these two things. You need to pick your u and your dv, and you need to plug into the formula that you would have had memorized, and that's it. Yeah.
Now, are there certain questions where it would be easier to pick more, like, can you give us an example like where it would be easier to choose a certain thing for u and a certain thing for dv? Or
That is a great question. In fact, I was going to ask you guys that question. How did I know to pick that as the u? What would have happened if we made the choice the other way?
It would have just been another hard integral.
Let's say I look at this same integral. Right? So I have my x e to the x dx. But now I said u is e to the x, and my dv is x. My du would be e to the x. My v would be x squared over 2. And so u times v minus the integral of v du would end up with that, which is correct, but that's actually harder than the original integral. I just actually made the situation worse on myself. Instead of having x times an exponential, I now have an x squared times the exponential. So it actually does matter how you make the choice. So yeah.
Could you keep it in that form if you did it like that? Could you keep
No.
it like, you have to
Like
take the
you would have to
integral out?
actually figure out how to integrate that, which that's a problem in and of itself. So yes, how you make this choice, it actually matters. Anyone know how you make the choice? How do you choose? Because this is actually worse. You don't want to end up in a worse situation. Well, long time ago, a lot of some guys sat down and they thought about all the possible situations and combinations and scenario, and then they came up with a mnemonic actually. The mnemonic is called Liate. So, aside from the integration by parts formula, when it comes to integration by parts, this is one other thing you have to memorize, the word Liate. And basically what this is a hierarchy. You kind of want to remember it vertically. L stands for logs, logarithmic functions. I stands for inverse trig functions. A stands for, quote, algebraic. But by algebraic, we really mean polynomials. But the doesn't really roll off the tongue, you know what I mean? So for A, T stands for trig functions, and E stands for exponential functions. There are other similar mnemonics. It actually doesn't matter if the T and the E can be swapped without much consequence, but you tend to want to do logs, inverses, and polynomials in this order. And here's how it works. To the top of the list, you get to be the U first. Moving down the ladder are the guys that get to be U last. Right? So this is the hierarchy of how you would choose your U. So Liate tells you how to choose U. It's called Liate. So what you would notice here for this function, for this example here, notice that I have two things being multiplied, an x and an e to the x. The x falls in the A category, while the e to the x falls in the E category. According to Liate, the A comes before the E. Therefore, this gets to be the U. So that's how you make the choice, according to this mnemonic. So you look at the two kinds of functions that you would have. There'll be a very specific way in which you're going to make the choice. The hope is, after applying the integration by parts formula, the integral on the right side is going to be easier for you to compute. And choosing in this order gives you the best chance of getting something that's easier to compute, even though it's not always going to work. Let's do another example. Integral of x squared times ln of x. Look at that example. It's a random integral. So you go through that thing in your head again. Does that look like a basic rule? No. Is there a way to simplify this? Not really. Can a substitution work? Well, what would you substitute? And you'd kind of get in trouble with all of those until you might think, okay, maybe integration by parts is going to work. Once you've settled on integration by parts being the method that you're going to choose, how do you make the choice? Who's the you? Yeah?
Would the u be ln?
U is going to be the ln. You're going to look at, these are the two functions present. This guy falls in the L category because he's a log. This guy falls in the A category because it is a polynomial. So that's your u. So knowing that I want to do integration by parts, that's going to be the choice. Set u to be ln of x. Set your dv to be the x squared. The derivative of ln is 1 over x dx. The integral of x squared is x cubed over 3. And then you plug into that formula. So it's going to be u times v minus the integral of v times du. Now when I multiply these two, the x cancels. Let me just write it. And what we're going to notice here is that this x is going to cancel into one of those x's. And so I would get x cubed over 3 ln x minus 1/3 times the integral of x squared dx. And look at that. The integral on the right side is a lot easier to compute than the integral on the left side. In fact, there's a basic rule that applies to this. That's just an integral of x to the n integral. So you add 1 to the power and divide by the new power. So this gives us x squared ln x dx is equals to x cubed over 3 ln x minus x cubed over 9 plus c. And that's your answer. Questions on this? We're good? Let's do another example. Which, that's true for this class more so than Calc 1. In Calc 2, you're going to learn a lot of new techniques, and so kind of the best ways to get them into your head is to just do a lot of drills. You just do example after example, and eventually something's going to click. It's going to feel very natural. But before you get to that point, it's all going to be very confusing. So let's actually do a few more examples. Let's do one that seems a little bit strange at first sight. Let's see how to integrate ln of x. Do we have a basic rule for that? Not yet. I mean, once we actually do this, it's now going to be a basic rule. But at the moment, we probably don't know how to integrate ln of x. We know how to differentiate it. The derivative is 1 over x, but we don't know the integral. So we don't have a basic rule, nothing to simplify to give us a basic rule. Substitution. A substitution actually could work here, but it'll actually be a little bit strange to actually get it to work. But we're going to do integration by parts. A substitution would actually lead you into an integration by parts. Maybe I'll show you that later, but maybe not. This is actually integration by parts. So how would you go and choose the parts?
You
Yeah.
use ln of x.
Right. So at first, it might look like, what are you talking about? What parts? There's one guy here. Of course, there's always a 1 there, isn't it? So you can think of 1 as a function, just think of the dx as one of them and the ln as the other one. So you can think of any function just standing on its own, you can automatically think of it as an algebraic function times that function. Now of course ln is the thing that we want to integrate, and we don't know its integral, we know its derivative, so it also just makes sense that ln would be our x, and our dv is just going to be 1 dx. du gives us 1 over x. Integrate 1, you get x. And so you plug into the integration by parts formula. U times v, this is x ln x, minus the integral of v times du. That's just going to give you 1. And the integral of 1, well, we know that. That's our answer. By the way, this is a very important problem, because from now on, this should be one of the things in your basic arsenal from now on. We declare it a basic rule. So from henceforth and forevermore, this is never something you should have to derive, it's just something you should know. The integral of ln x is x ln x minus x. Some things are just, they show up often enough for you to just have it memorized, and it makes your life a lot easier. So there are times when integration by parts will work in this kind of a sneaky way. Basically, if there's only one function, you can just think of the other function as being 1, which is a polynomial, and then just apply the integration by parts on the function by itself. Do you have a question? Okay, you're just stretching? Okay. Here's another example. Let's say I wanted to find the integral of tan inverse of x, or arctangent, as you might have learned it. This is another one where there is just one function there. You probably didn't learn how to integrate tan inverse, I don't think, in Calc 1, because by parts is pretty much the way you would do it. You would just choose that, the tan inverse, as your u. What's the derivative of tangent inverse?
1 over 1 plus x squared.
1 over 1 plus x squared. As far as inverse trig functions go, I would expect you to know about the inverse sine and the inverse tangent, right? So you should know how to differentiate them and integrate them. I'm not really ever going to ask you about the others. So just in case you want to know what do I have to memorize for this class, you need to know about the inverse tangent and the inverse sine function in terms of the formulas. The v would be x. So, u times v minus the integral of v du, and we end up with that integral. Is that easier? How would you integrate that?
Do by parts again.
What would the parts be?
X and 1 over 1 plus x squared.
Who gets to be who? Who's the u?
You would be the 1 plus x squared, right?
How to make u x and then couldn't you
just do the integral of x minus the integral of 1 plus x squared?
No? Why? You can't. That's not.
could you do by parts again then? And then
You could, but I wouldn't.
okay.
I don't think you could. That's way more trouble than it's worth. So, what I started writing down at the beginning, it is always the guide. Every time a new integral shows up, you go
Simplify.
through the same thinking. So I said a new integral popped up in me computing this integral. What do you think about? Basic rule. Does this look like a basic rule? No. Can I simplify it to look like a basic rule?
Oh, you can do use of.
Right. But
Sorry.
the answer would be no. Then the third thing you would think is substitution. Is a substitution going to work? Yeah. That's a substitution. I substitute the denominator. The derivative of that gives me the numerator. So here I would just do a regular substitution. So I would do a substitution. So this is a problem that starts out as an integration by parts, but it leads into another technique. There's no rule against stringing techniques together. So, I mean, there's a chance of getting confused if you start off with a substitution and then go into integration by parts because you reuse the variable. But at this point it's okay because I only have x's here. So I'm going to use the u again, but this is a u from a substitution, not the u from the integration by parts. You can say u equals 1 plus x squared, and my du would be 2x dx. So 1/2 du is going to be my x dx. And so this new integral is going to be minus 1/2 times 1 over u du. And that is going to be minus 1/2 ln of u, absolute value, plus c. And then I go back and I plug that in. So this would mean that the integral of tan inverse of x dx is going to be x times tan inverse of x minus 1/2 ln of 1 plus x squared. Now, technically you don't need the absolute values here, but you don't want to forget them when you do need them, so I'll just leave it in. Starts off as integration by parts, leads into a substitution. This is what will start to make things confusing. Sometimes you start off in one technique and you need another technique to help you out, but at the end of the day, whenever an integral shows up, you always go through the same thought process. Start over from the beginning. Can I use a basic rule? No. Can I simplify? No. Can a substitution work? Always the first three things that you look at when you're faced with a random integral. So that's your answer here. Let's do another example. More examples, more examples. Okay, integral of e to the x sine of x. Now here, that's an e. Here, that's a t. According to Liate, we're going to choose the t as the u. But like I said, the e and the t are all interchangeable. If you mess up here, it's not that big of a deal. But to follow Liate, I'm going to choose u equals the sine of x, and my dv equals the e to the x dx. My du is going to be, I'm taking the derivative, cosine of x, and my integral of here is going to be e to the x. Then I'm going to get e to the x sine x dx is equal to u times v minus the integral of v du. So we end up with that. So in order to compute that integral, I'm going to have to compute this integral. Can we do that? How would I do this integral? E to the x times cosine.
I agree.
Yeah?
By parts.
By parts again. Okay, so we'll do by parts again. All right, so that here is an e, that here is a t. So I'm going to do u equals the cosine of x, du equals minus sine of x, my dv equals the e to the x dx, my v equals e to the x. So now I'm going to plug that in. So this would become e to the x sine of x minus, open parentheses here, parentheses, very important, u times v, e to the x cosine of x, minus the integral of v du, but it's minus a negative, so that becomes plus e to the x sine x dx. Wait, what just happened?
I think you made
No, it's
Yeah.
fine, because you have.
It's fine?
I see.
Yeah.
I
Yeah.
think it's e to the x cosine x, or am I wrong?
Where, here?
No, outside, the first term.
No, it's u times v. So that's fine.
So if you distribute the negative,
Yeah?
that whole side's equal to integral.
Yeah. Notice how we got the original integral back.
So you can just.
Right, which at first you're like, what the hell? But notice that now, it's just like an equation where there's one thing that you want to solve for. Just move that to the other side.
Divide by 2. And that's,
So I'm going to move that to the other side and divide by 2. So here's an integration by parts. This is a, well, I wouldn't say a common scenario, but it's one of the important scenarios. Sometimes you're doing an integration by parts and you'll actually end up with the same integral that you started with. This usually happens with when you have exponentials and trig, or anything that eventually when you keep differentiating it eventually comes back to itself. What you can do, sometimes people do this, they just give it a letter name, so they'd call this I, and say they realize that they have I equals e to the x sine of x minus e to the x cosine of x minus I. You would add I to both sides, you'd have 2I on this side, then you divide both sides by 2, and you just put in a plus c because you know it should be there. One half of this guy. And that's your answer. So this is a revolving integration by parts. That's not an official name, that's just what I like to call it. Because it revolves back to itself eventually. But whenever that happens, you don't freak out, you just move it to the other side. So that's a nice example, common example. Here's another example. And these last two examples especially kind of lead into something I want to do next class. What if you had x squared e to the x? Well, of course, you go through the same rules. Basic rule, no. Can I simplify it? No. Substitution, no. It doesn't help. Okay. Integration by parts is what you would choose. That's an A, that's an E. According to Liate, that gets to be your U. So you would do U equals x squared, dv equals e to the x dx, your du equals 2x dx, your v equals e to the x. This is equal to u times v minus the integral of v du. You end up with another integral, which is the integral of x e to the x. But we've dealt with that before. We actually know how to do that. That's another integration by parts. So we do another u equals x, dv equals e to the x dx, du equals dx, v equals e to the x. You do the u times v minus the integral of v du. You would end up with x squared e to the x minus 2, open parentheses, u times v minus the integral of v du. Now eventually, with persistence, we've broken this integral up into that, and then we've broken down that integral into that. Ultimately, we end up with an integral that's easy for us to solve. So this is going to be x squared e to the x minus 2x e to the x Integral of e to the x is just e to the x, so this is going to be plus 2e to the x plus c. So, integration by parts, sometimes it can be something that one shot, after one step, you got something nice. Sometimes you can lead into an integral where you need another technique like a substitution. Sometimes it revolves on itself, in which case you just solve for the other guy. And sometimes you just have to repeatedly use integration by parts until you just break it down slowly. You break them down until you can get to an answer. What if I had x to the 5th e to the x?
Are we gonna do tabular next?
We're going to do tabular next because, as you can probably tell, that's going to be super annoying. And that kind of next time. Tune in next time. Because I think we're out of time now. But that's the basics of integration by parts. You know how to do it. But sometimes it can be a little bit annoying. So we're going to come up with a refinement of the technique, which I'll show you guys next time, and then we'll do a bunch of examples. And then we'll move on to another technique. So the first part of the class is just us learning a bunch of new integration techniques. It's going to be important for this class in the future. I will see you guys on Friday.